I will be talking about gravitational waves, and since this is a topic that is slightly aside from the rest of the topics in this school, I'm putting out some references. The first two are standard textbooks on gravitational wave science, astronomy, physics, what you want to call it, and the third link there is a review article mainly focused on data analysis of gravitational waves. So much of my lecture is also based out of these notes. If you want, you can go back and have a look at some of these references later. In order to keep the program interactive, let me first ask you, how many of you have seen this plot? I guess most of you have seen this plot. So this plot is the plot associated with the first direct detection of gravitational waves, the discovery of gravitational waves from the merger of a binary of two black holes. The two black holes, they go around each other. As they go around each other, they emit energy. As they emit energy, they fall in closer to each other. So they spin faster and faster. Eventually they merge, and in the final stage, it rings down, it emits the last bits of gravitational waves and settles down into a final black hole. We call that phase the ring down. And I just mentioned that as the gravitational waves are losing energy, as the system is losing energy, it's falling in closer, with the two black holes are falling in towards each other, and they're moving faster and faster. If they're losing energy, they should move more and more slowly, right? Why are they moving faster and faster?
Is it a question to ask?
Is it the
question to ask? Or
yeah, that's a question. That's a question for you to answer.
Yeah, because the total energy is equal to the half of potential energy.
But because it's a gravitationally bound system, and we cannot just talk about total energy. We cannot just talk about kinetic energy. We have to talk about the total energy, which is sum of the kinetic and the potential energy. And as the black holes are, we know that in a gravitationally bound system, the total energy is negative half of the kinetic energy. So if the system is emitting energy, that actually has to fall in close to each other. Okay. Let me show you another plot and ask you how many of you have seen this plot. Most of you. And for those of you who have not seen this plot, this is a plot associated with the first indirect detection of gravitational waves, which came from the Hulse-Taylor binary pulsar. And what happened was Hulse and Taylor, they observed that the pulsar was slowing down exactly at the rate that was predicted by certain calculations, certain post-Newtonian calculations. And this demonstrated that gravitational waves really exist. And this is important because for a long time people didn't know whether gravitational waves existed for sure. Good. We will come back a bit to both the emission process of gravitational waves, to the waveform of gravitational waves, which we saw in the previous slide, as well as to pulsars in a slightly different context later in the talk. But let me first give you a broad plan today. The first lecture is going to talk about the key aspects of gravitational waves, and you will see that it stands on three pillars: theory, experiment, and data analysis. So I'll talk a bit about theory, I'll talk a bit about experiment, and I'll talk a bit about data analysis. And in the next lecture, I hope by the end of the next lecture, you will understand why a gravitational wave module is very, very relevant for a course on cosmology. Good. If you have any questions, please stop me and feel free to ask. I'll be very happy to answer. Let me ask you a question. Once again, I know that all of you know the answer to this. What are gravitational waves? All of you probably have the same answer. They're ripples in the curvature of space-time. We're talking about curve of space-time. So we're talking about general relativity. And in Einstein's general relativity, the curvature of space-time, which essentially sits in the left-hand side of Einstein's equations, is dictated by matter. What is sitting on the right-hand side of Einstein's equation via the stress tensor. The right-hand side of Einstein's equation is the property of matter. The left-hand side is the property of space-time. And the coupling that couples matter to space-time, the gravitational coupling, is 8 pi g over c to the 4. 8 pi g over c to the 4, if you compute g over c to the 4 in any units, it's going to be small. Okay, other than in units where g is 1 and c is 1, then it's not going to be small. But in in more physical units, it's going to be a very small number. This already tells us that gravity is a very, very weak force. Good. It's very intuitive to think of the Einstein equation as some kind of a Maxwell-like equation. In Maxwell's equations, you see the electromagnetic field sitting on the left-hand side, and you see the charges and the currents, which are the sources sitting on the right-hand side. And you also have a coupling constant there. It can be, depending on the units, it can be the charge of the electron. Depending on units, it can be epsilon naught. Depending on units, it can be the fine structure constant. But this gravitational coupling is much smaller than the fine structure constant. I just said that the left-hand side is like electromagnetic field. So what do I really mean by a field? So in this case, in Einstein's theory, the space-time itself is like a field. It's more proper to say not the space-time itself, but the curvature of space-time is a field, and the curvature is governed by the Riemann tensor, which can be derived from the metric. What we see on the left-hand side is the Ricci tensor, which can be obtained from the Riemann tensor. Good. This was a lightning introduction to general relativity. The fact that these are like Maxwell's equations already hints that maybe there are wave-like solutions. We know that Maxwell's equations have wave-like solutions, and that has the fantastic association that these electromagnetic waves are indeed what we see as light is definitely one of the major successes of physics, and that is now associated with all of astronomy. So it's quite natural to ask whether general relativity also has wave-like solutions. And in fact, if one takes general relativity, if one takes small perturbations about a flat background, so one takes g mu, which is the metric which tells us how space-time could be curved, and eta mu is the flat space-time. On top of that, one adds a small h mu, and h mu is much smaller than 1 being the components of eta mu. And if one then makes some transformation of variables, one constructs the trace reverse metric, where the trace goes from goes to the other side. This h bar, quantity h bar, has trace 0. And one sets some gauge, just like in electromagnetism, you have gauge transformations. In general relativity, you have gauge transformations. When you study radiation, you talk about Lorentz gauge, not just radiation. When you talk about Maxwell's equations, you have Lorentz gauge. You have a similar Lorentz gauge for gravitational fields, you switch to the Lorentz gauge, and you can obtain a wave equation for the metric, just like you obtain the wave equation from Maxwell's equations. Okay, good. Now, general relativity is of course more complex than Maxwell's equations because there are a number of different components of the metric. It's difficult to count the exact degrees of freedom. It turns out that there are two physical degrees of freedom, and all the other degrees of freedom are gauge degrees of freedom. It is possible to transform to a gauge after fixing the Lorentz gauge. There's still some gauge freedom left over to transform to something called the TT gauge, the transverse traceless gauge, where for a wave propagating in the z direction, one is left with only transverse components x and y and traceless. So we see a transverse metric, we see a small transverse submetric here, h plus h cross minus h plus, and you can see that the trace is 0. The diagonal components add to 0. And in this transverse traceless gauge, in this gauge, it's clear to see the two independent degrees of freedom. And the two independent degrees of freedom are the plus and the cross polarizations. The plus polarization because it looks like a plus in the xy direction, and the cross polarization because it looks like a cross not in the xy direction but in the 45-degree directions. Quick question. In light, we have very similar two polarizations, the x polarization and y polarization for a wave propagating in the z direction. Why do we not have x and y polarizations but plus and cross polarizations for gravitational waves? What is the answer? The answer is out there on my slide. The answer is, this is because unlike light, which is a vector spin 1 field, gravitational waves is a tensor spin 2 fields, which is the reason why if you rotate by 45 degrees, you go out of phase, and if you rotate by 45 degrees, you go to the other polarization. If you rotate by 90 degrees, you are out of phase, and if you rotate by 80 degrees, you go back to the same phase that you were in. Good. Now, with the gravitational waves, we came up with some wave degrees of freedom, right? Whether wave degrees of freedom are really significant or each artifacts have used many people, including Einstein. Einstein's story is like Eddington of the famous Eddington important gauge artifacts in the quantity of gravitational waves. In a 1936 paper, Einstein together with a dozen of PR claims that gravitational waves does not exist. And they submitted this paper, physical review back then. You can say the physical review, not key like you have now. Robertson, Robertson metric was the reviewer of the paper. Robertson was convinced otherwise, and essentially, Robertson came up with some objections to Einstein's argument in the paper and sent it back to Einstein. Einstein was not really very comfortable with getting negative reports, so he decided to. He didn't argue with the reviewer. He believed that what he had written was correct, but he decided never to submit a paper. He did it to the reviewer again. However, Robertson, who was really convinced, he eventually, via infill, managed to convince Einstein about the fact that about his own reasoning. Much later, 20 years later, Pirani could come up with a coordinate-independent description of gravitational waves. So we were moving towards a situation where we could give more and more weight to the existence of gravitational waves. And in the 1957 Chapel Hill Conference, Feynman finally demonstrated that gravitational waves could transmit energy. Now, that is the crucial difference between something being physical and something being a gauge artifact, right? If you're transmitting energy, then you have to be a quantity that is physical. As soon as this was demonstrated, people started coming up with ideas for gravitational detection. The first ideas were resonant bar detectors. So as a gravitational wave would pass through a huge mass, a bar or a huge sphere would start resonating at the frequency of gravitational waves, and one would measure the resonance. And actually, Weber came up with a number of positive detections of gravitational waves back in the around the 80s. I forget the exact date here. Most probably, I mean, we now know that Weber's experiments, something must have gone wrong, because the kinds of detections Weber was getting, we cannot observe, we cannot expect from any known sources. So something must have gone wrong. However, his efforts stimulated others to come up with various other ways of directly and also indirectly detecting gravitational waves. And finally, in 1975, Hulse and Taylor discovered the binary pulsar, which eventually showed for sure that gravitational waves exist. Okay. So how can we detect gravitational waves? We already talked about two ways. We talked about LIGO that has detected gravitational waves. Now I'm talking about direct detection and not indirect detection, such as the binary pulsar. We talked about resonant detectors. How are we going to detect gravitational waves? So one can think of trying to measure gravitational waves with something very rigid, like a ruler. So you have a rigid object like a ruler. What would happen to the rigid object when a gravitational wave is trying to pass through? The gravitational wave will try to squeeze and stretch the ruler, so the gravitational wave will try to increase the stress, change the stress within the ruler. It turns out that this is not really measurable, the stress within a rigid object. So the ideas of the resonant mass, it's not practicable for detection, or at least terrestrial resonant detectors are not practical for the kinds of sources which you observe. But this idea has recently resurfaced, and there are some very primitive concepts of trying to use the entire moon as a resonant detector. So as the gravitational wave is going to pass through the moon is going to resonate, and different seismometers across the moon, they are going to resonate with the moon, and one can measure the distance between them and measure the gravitational waves that are passing through the moon. So this idea is slowly resurfacing. Maybe it will be a reality some decades from now. The way LIGO and Virgo they currently measure gravitational waves is they do not try to construct a rigid object like a ruler. They do not rely on resonance, but they want to make the objects as free as possible. So one has mirrors at the end of these LIGO experiments. There are very heavy mirrors which are as isolated from the Earth as possible, so that they freely respond to gravitational waves. They do not resist the gravitational waves. They just move along with the gravitational waves as the space-time is stretching and squeezing. And they act effectively as freely falling masses. The animation you saw some time back, the plus and cross polarizations, that's how a ring of freely falling particles would behave. So if you have test masses aligned like that, then they would also move as gravitational waves are passing through. This is the current detection concept. Is there any other detection concept that you can think about? So So instead of relying on this apparent length contraction, one can think about time dilation. So we know that pulsars are very precise clocks. They tick at a very precise rate, and there are pulsars out there. When gravitational waves are passing through a field of pulsars, they would slow down some of the pulsars and speed up some of the other pulsars. So if one is able to measure the slowing down and the speeding up of the ticking of these pulsars, one should be able to detect gravitational waves. So these are the different detection concepts. Next question is what we're trying to detect. We are trying to detect here a relative deformation or strain. This H, the quantity which we saw in the expansion of the metric, is the same as the delta N over L, the relative deformation, and that comes because of the way you expand the metric. The question is, how small is this strain? The answer is the strain is once again G over C to the 4, the huge quantity, multiplied by the second derivative of the quadrupole moment tensor. So this equation tells us that we need a change in quadrupole moment in order to generate gravitational waves. Recall in electromagnetism, we need a changing electric dipole moment in order to generate electromagnetic waves. A changing quadrupole moment suppressed by G over C to the 4. So any changing quadrupole moment, if I shake my hand like this, I'm generating gravitational waves. But how much gravitational waves am I generating? We can try to do some order of magnitude estimates. If one takes a mass of 1 kg, 1 kilogram, keeps it at a distance of 1 meter, and rotates it with the angular frequency of 1 hertz, then putting in the constants, the number you get for the strain is 10 to the minus 53, a very, very small number. These are the numbers that one would produce or terrestrially with any kind of terrestrial gravitational wave generation mechanisms. Let's talk about what we have detected by the LIGO experiments. We are back to our first plot. If you look carefully, you should be able to read off the number for the observable strain on the vertical axis. And what's the number that we see, that you see over there?
10 to minus 20.
10 to the minus 20, 10 to the minus 20, 10 to the minus 21. So those are the strains that we are actually able to detect. That is also a much, much smaller number. It's really an amazing experiment that is able to detect such small relative deformations. 10 to the such small relative deformations. Okay. Before I move on to the experiment, there's one other slide full of equations which I'm going to talk about. This is the intensity of gravitational radiation. Once again, if you recall in the chapter on electromagnetic radiation, you will recall a Larmor formula. It gives you the total intensity radiated, and in case of the electromagnetic radiation, it turns out the Larmor formula is the square of the second time derivative of the electric dipole moment. In case of gravitational wave radiation, the Larmor formula is the square of the third time derivative of the gravitational quadrupole moment, which is the moment of inertia. And again, we can put these numbers in for typical sources. The energy that is emitted for typical terrestrial sources will be of the order of 10 to the minus 53 watts. Again, a very small number. So if I'm shaking my hand around, I'm not really emitting any energy in gravitational waves. With this, let's move on to the gravitational wave detectors, and LIGO detector as as an example detector here. The LIGO detector is 4 kilometers long, and we are talking about a strain of the order of 10 to the minus 21 or so. A strain of the order of 10 to the minus 21 multiplied by 4 kilometers is an absolute deformation of how much? 10 to the minus 21 times a kilometer, 10 to the 3 is 10 to the minus 18 meters. So the LIGO detector is able to measure distances to an accuracy of 10 to the minus 18 meters. And how small is 10 to the 18 meters? How small is an atom?
Angstrom?
10 to the minus 10 meters angstrom. How small is the nucleus of an atom?
Minus
A Fermi or so, 10 to the minus 15-ish meters. So we are measuring with the LIGO interferometers, we are measuring distances that are 1,000 times smaller than the nucleus of an atom. Extremely tiny distances. What is happening? So we can, what happens to the LIGO interferometer? Probably all of you are familiar with the concept of interferometry. There's a laser that's shooting out some light. The light is going into, this is the beam splitter, it's not labeled. Half of the beam is going in one direction, half of the beam is going in the other direction. They are coming back and they're interfering. One is able to observe the interference pattern. From the interference pattern, one can say whether these two mirrors, whether these two arms have an arm length that lead you to a constructive interference or a destructive interference. So, what could be how do you calculate the sensitivity of such a device?
By looking at the interference pattern?
By looking at the interference pattern. So if I tell you that I have an interferometer that is, let's say, 1 kilometer long, the X arm is 1 kilometer and the Y arm is 1 kilometer. How small distances can I measure with a 1 kilometer detector? Yeah. How would we do that calculation?
So we need a wavelength of light.
We need the wavelength of light. That is going to give us the number. Let's do the calculation very quickly. What is the wavelength of what is the typical wavelength of light that we use? I mean, we usually use optical or infrared lasers. So it's 4,700. Let's just make it 1,000 angstroms for an order of magnitude calculation, and let's so 1,000 into 10 to the minus 10 meters. So that is about 10 to the minus 7 meters, and the length of the arm would be as I said, is 10 to the minus 3. 10 to the plus 3 meters. So if we say that we have a very poor sensitivity, we are able to distinguish only a crest from a trunk and not anything in between, then the sensitivity of a detector is going to be 10 to the minus 7 over 10 to the 3. So we are going to detect strains of the order of 10 to the minus 10. Okay, 10 to the. However, one is of course more sensitive. one cannot, one can tell not just the crest from the top, but one can also see how the intensity is changing within the interferometer. So one is going to have better sensitivity, and that is something that we cannot quantify by this order of magnitude calculation. One can of course say that by eye we can be sensitive to about 1/10 of the difference of the total intensity, but we are of course not using our eye, we are using photon detector. So we have to decide how well a photon detector can count. So that is going to give some improvement. The other major improvement that comes here is from the fact that what we are using in the arms, they are not, the arms are not really simple interferometers, but they are something called Fabry-Perot cavities. And in a Fabry-Perot cavity, what happens is that effectively the light bounces back and forth many, many times, increasing the arm length by a factor of 1,000 or so. So about a factor of 1,000 comes from the Fabry-Perot, and the rest of it comes from photon counting. And with this, we are actually able to reduce this number from 10 to the 10 to 10 to the minus 10 to 10 to the minus 21, which is really fantastic. Good. So in a detector, we have noise. In these interferometric detectors, we have three dominant kinds of noise. We have a quantum noise, which dominates at high frequencies, and this quantum noise essentially comes from photon. It comes from the photon counting. The thing is, if one tries to reduce the quantum, the counting noise in some other way, then some other noise increases. It's just like an uncertainty principle, so it's very difficult to reduce the quantum noise unless one goes over to squeezing techniques, which are very making some states which are sensitive to certain phases of light, certain speed states of light. At intermediate frequencies, what dominates is thermal noise. Thermal noise, what is thermal noise? You're shining a very high power laser. You need a very high power laser in order to be able to measure photons properly. And if you are shining a high power laser, then you're heating up the mirror coating. As you are heating up the mirror coating, they're moving around with the Boltzmann with the thermodynamics, and that is producing some thermal noise. That is what dominates at intermediate frequencies. And at low frequencies, one is the most dominant noise is the terrestrial noise, which one gets from essentially all the vibrations. And in trying to reduce the vibrations at higher frequencies, one automatically increases the terrestrial noise at lower frequencies. That's how it works. So one ends up with this sensitivity curve. So this is the sensitivity curve. At what frequencies are we the most sensitive to? Are we most sensitive to at frequencies of 10 hertz, 2000 hertz, or somewhere in the middle? All of you are convinced that this is where we are most sensitive to, so this is the noise that we are talking. So wherever the noise is low, we are more sensitive. Whenever the noise is high, we are less sensitive. Noise is very high at frequencies of 10 hertz, noise is going up. At frequencies above 1000 hertz, our sweet spot is this kind of 100, 200, 300-ish region. Good. And even here, the strain, it is, no, this is not really the strain, but this is in some sense the strain density. If you integrate this over the frequency, then you would obtain strain. So this is not quite the strain. You have to take the 10 to the minus 23 and essentially multiply it by 100 or 1000 to actually get the strain. So the strain is indeed 10 to the minus 21. And we have to get a signal out of noise, which is itself of the order of 10 to the minus 21. Very often a signal will be much smaller than the noise. So not only do we need a sophisticated experiment, but we also need sophisticated data analysis techniques. What kind of sophisticated data access techniques do we need? One of the most commonly cited examples is the concept of matched filtering, which works only for model signals. So here you can see a signal which is in red, which is buried in the noise, which is in blue. So the red signal is already there in the noise. You do not see it just because the noise is much larger than the signal. But you kind of know what kind of signal you want to look for. So you use a template, and this template comes from theory. So you see how theory comes in. You need theory to come up with a template, and then you run this template across the data, which is in blue, most of what is noise. And when you run the template through the data, here you see an animation. You see almost nothing. But at a certain point, as soon as the template matches with the signal in the data, you see a spike in the correlation function. And this is how you know that there is an interesting signal over there. This is how you search for example, compact binary mergers for which you can have waveform models. So you use some kind of waveform model, run it to signal. If there's something interesting, you see a match. I'm going to talk a bit about this later also. But let's talk about some other kinds of sources which we expect to see in gravitational waves. What are the sources that we expect to see in gravitational waves? So, question from the first part of the lecture. What is the most crucial feature that you need in order for something to be a gravitational wave source?
Mass.
Mass, but if there is mass, if there is just mass, would you see gravitational waves? Not really. Quadrupole moment, not just quadrupole moment. It's a changing quadrupole moment. So there has to be a changing quadrupole moment. And as you can see for a compact binary merger, there is indeed a changing quadrupole moment. So that's why they emit gravitational waves. There can be other objects where the quadrupole moment also changes. For example, if there is a neutron star, and the neutron star is not exactly ellipsoidal, but it has a tiny hill on top of it, then if this neutron star is rotating, because of this hill, there's a changing quadrupole moment. Essentially, if there's a changing quadrupole moment, then the silhouette of the object changes. So, whenever the silhouette of the object is changing, you know that the quadrupole moment is changing, more or less. And so, this kind of a source, a neutron star, so it should emit gravitational waves. Now, it turns out that the gravitational waves that it emits would be, because it's spinning at a certain rate, a neutron star, the gravitational wave that it would emit is monochromatic. The total amount of energy that is being radiated away is much smaller in this case compared to the total rotational energy of the system. So the system does not spin down, the system does not slow down or speed up that way. The system does not slow down that much. So you observe a very continuous source. So you observe a monochromatic gravitational wave from these sources. The advantage of continuous waves is that you just need to look for a single frequency. So you just look for one single frequency. If necessary, you can just make a detector that is sensitive to that frequency. For some neutron stars, you do really see the neutron star that is rotating at a certain frequency. So you can look for gravitational waves. Another question. If you see a neutron star that is rotating at a certain frequency, at what frequency would you look for gravitational waves from the neutron star? Let's say a neutron star is rotating with a frequency f. Double. And once again, what's the reason? The reason is because the gravitational field is a tensor field, it's a spin 2 field. So you would see gravitational waves at twice the frequency. So just search for that at twice the frequency, and you might be able to observe something. And you can take very long stretches of data. You can take huge stretches of data if you want. and you can search for this single frequency. As you take longer and longer stretches of data, you build up signal, while noise, which is a essentially a random quantity, the signal to noise ratio goes down as you take longer and longer stretches of data. You can also expect gravitational waves from explosions, and the most common explosion is a supernova explosion. Yesterday we heard about type 2 and type 1 supernovae. So what kind of supernovae would explode? The core collapse supernovae. So because the other kind of accretion supernovae, they are very symmetric. They don't lead to, because they're symmetric, they don't lead to that much of gravitational waves. The quadrupole moment, the associated quadrupole moment is smaller. However, in a core collapse supernova, there is a significant asymmetry in the quadrupole moment that may lead to a detectable gravitational wave if the supernova is going off close enough. By close enough, I mean within our galaxy. Good. Finally, one last slide before I move on to the second half of my talk on the observation band of gravitational waves. So here you see our terrestrial band with I think it's a LIGO Virgo sensitivity curve, one of the next generation sensitivity curves. I'm going to talk about this a bit in the second lecture. The observed signals like GW150914, the first detection, some of the other expected signals from core collapse supernovae, from rotating pulsars. These are things that we haven't observed yet, but may be observable. So this is more or less the ground-based band around 100 hertz. We can stretch it down to a 10 hertz, maybe 5 hertz, but not more than that, not below that. Then we can have we have the space-based band, which would be something like the LISA, and because the LISA detector is much bigger, so we are looking at much larger lengths. So we are looking at much lower, essentially, frequencies. So the LISA is sensitive to millihertz to essentially in the millihertz band. And finally, the pulsar timing, which is sensitive in the nanohertz band. And in LISA, you would see supermassive black hole binaries. These are some of the exciting LISA sources, extreme mass ratio in spirals. While in the pulsar timing band, you would probably see even the stochastic gravitational wave background. In my previous slide, I forgot to tell you one of the important things I wanted to mention. Other than these three resolved sources, there's also the stochastic gravitational background. The stochastic gravitational wave background, a part of it can be cosmological, a part of it can be primordial, can be from the very early universe, but a large part of it would be drowned by all the other sources that you see in the late universe, binary black holes, also all kinds of supernovae and other sources that would lead to a incoherent superposition, which you would also see in this stochastic background. And some part of the stochastic background, largely could be observable by these pulsar timing experiments. So this was a quick overview of gravitational wave science. After this, I'm going to, for the next half, I'm going to concentrate mainly on compact binaries, compact binary mergers. Okay. Since I'm about to switch topic, let me ask if you have any questions at the moment.
From this,
Yeah.
Side so steep. Okay, so we see this, I don't know, it's again in error, or what do these black lines represent?
Oh no, it's just it's a different okay. It's a different detector concept, right? So that's just a lower limit coming from something that I'm not very aware of. I have to admit. Oh, this lower edge, right? Yeah, I'm not sure why it comes. It's not.
Okay, and I guess for them, then we have the machine perturbation theory around FRW, not the planet.
Yeah.
Do we expect these stochastic backgrounds to be detected in the LIGO Quickly, as we are, you also have five different
Yeah.
and do we have any plan and plans for like photographs?
So the radio observations are pulsars, by the way. And with these pulsars, you are able to, with these pulsars, you would be able to detect gravitational waves in this nanohertz. Okay, so the modulation, the pulsar frequency would be in the nanohertz band. Okay. I won't answer that question. Other questions?
The reason for stochastic background are just random astrophysical processes or something.
A part of it would be primordial. So primordial means coming from inflation, which could be associated with exotic models such as cosmic strings. So cosmic strings can collide even much after inflation. Then I guess but there's also going to be an astrophysical part of the stochastic background, which may dominate the cosmological part, which may dominate over the cosmological part definitely at high frequencies. Usually the frequency dependence of these, the astrophysical and cosmological components is slightly different. If you go to lower frequencies, the relative strength of the astrophysical component will go down. So if you want to look for something that's cosmological, you should go to very low frequencies. But at high frequencies, you will almost certainly be dominated by astrophysics.
I think that will be the reason to be detected by SCAR, the astrophysical part, because SCAR mostly is in radio, if I understand. And I'm just
No, SAA will act exactly as the EPTA. EPTA, the pulsar timing array, is an array of radio observatories, and the pulsars, it's just like in the LIGO. I mean, you see there are mirrors and the tracing, I mean, the interferometer. So we may imagine that the pulsars are just like these test masses, mirrors, but they are sending active signals. And what is happening on road, we are detecting and able to smartly disentangle. So EPTA is based on the already existing array of radio telescopes, and in the same way the SKA could be used, yes.
Yeah.
Talking about these deltas, so of course to generate that we have to know or assume something about the origin. And my question is, can it be that there is a degeneracy that's a different origin can represent the same result?
I will try to answer that question after the next part. I'm going to answer that question. You should remind me if I don't. Other questions? Let's move on to the next part. Then the next part is specifically about compact binary coalescences, and I will just outline a simple calculation of obtaining the compact binary waveform. I will sketch it. I won't go through the whole of it. It essentially boils down to solving a two-body problem in general relativity. Now, you know that in Newtonian mechanics, the two-body problem is solvable. However, in general relativity, the two-body problem is not exactly solvable. You have to solve it by some kind of a perturbation theory. So this is the first order of that perturbation theory, or maybe the 0th order of the perturbation theory that you are doing. It's just a two-body problem. So you have one mass, another mass, they're going around each other, and this is the angle between some reference axis, and you assume that the angle is a function of the angle just increases linearly with time, 2 pi ft. So it's trying to execute circular motion. So what you would do is First, you can construct the moment of inertia tensor, and this moment of inertia tensor looks like this. Here, mu is the usual reduced mass, which you are familiar with, and I showed in a previous slide that the gravitational wave strain is proportional to the second time derivative of the moment of inertia tensor. These quantity phi definitely depends on time. So the moment of inertia tensor depends on time. You take the second time derivative and you obtain this gravitational waveform as a function of the gravitational waveform as a function of certain parameters. Here, the waveform has been evaluated at a distance d from the source, so that's why you have a d dependence in the denominator. dl is the luminosity distance, and you have written out this in terms of the total mass. And again, gravitational people working on gravitational waves, they like to define a number of different kinds of masses. Already, other than the reduced mass, you see the total mass here, and something called the symmetric mass ratio, which is the product of the two masses divided by the square of the total mass dimensionless, and it's a ratio, that's why it's symmetric between m1 and m2, so it's the symmetric mass ratio. And we have already discussed why the GW frequency is twice the orbital frequency. So essentially one can obtain the waveform solely by working out this problem and using this expression. And one can also calculate the total energy that is radiated. One can use the Larmor formula and obtain this as the total energy, as the total intensity of radiation. Simultaneously, the Newtonian energy of the system turns out to be half of the reduced mass times this quantity squared. So pi gm gravitational frequency to the 1/3 that acts as some kind of a velocity, and that's also very you see that almost everywhere in the post-Newtonian expansion. So this is just called the Newtonian velocity. So the quantity within parentheses times 1/3. This looks like half mu v squared. And then you know that this is the Newtonian energy. This is the rate at which energy is being lost. You just use the energy conservation. And from energy conservation, if you plug this back into this equation, if you plug this and that back into this equation, you see how the frequency of gravitational wave evolves with time. And the frequency increases with time, given by a solution of this differential equation. You can compute the time. You can show that in a finite time, any spiraling system is going to collapse. It keeps emitting gravitational waves from any frequency. It takes a finite time to collapse. As the system collapses, the frequency blows up, becomes infinite. After that, of course, there's no gravitational waves. And here we have defined yet another mass, and this is very important for gravitational wave observations, this chirp mass, which is a very peculiar combination. Nobody else could define this kind of combination of mass and people working on gravitational waves. It turns out that this chirp mass, the leading order, tells us how fast the system essentially inspirals. It dictates the inspiral of a system, so we define this quantity. And this is the leading order. This is the leading order of the post-Newtonian expansion. What one can do is one can keep expanding in powers of v over c, when v is the Newtonian velocity, 1/3 of the quantity that appears in the parenthesis out here, and one can compute up to 1, 2, 3. What is currently happened is people have computed up to v over c to the power 7 at the moment, and that's called the 3.5 post-Newtonian order. If you look at the expression, I think it takes 2 pages in a normal readable font on A4 sheets, and if you want to put in spin corrections and other corrections, then it becomes even longer. So, using these, it was these expressions that essentially went in. I also didn't talk about something called eccentricity, which modifies this expression and is quite important, particularly for this Hull-Scalar binary. If one puts in all those expressions together, one can compute exactly the way the energy will be lost, and that exact energy loss was measured in this particular experiment. Okay. Now we are coming close to answering the question that was asked earlier. So we need to start thinking about what the parameters of magnets. We already talked about the masses. So there are the component masses, of which there are two. There are two component masses. You can talk about the two masses M1 and M2, or you can come up with a combination. So people often come up with a mass ratio and the Chuck mass, sometimes the symmetric mass ratio and the total mass. So essentially there are two independent masses. There are the two components of the binary. They could themselves be spinning. So each of them has a spin angular momentum, and we usually rescale the angular momentum with the square of the mass so that the spin has a maximum value of 1. If in these units, if this parameter s is greater than 1, then that starts violating the cosmic censorship. One would not see black holes then, but one would see naked singularities if this S is greater than 1. So for these objects to be black hole, S has to be smaller than 1. But be aware for neutron stars, this quantity S has no such restriction. However, for practical purposes, the spin variable is much smaller than 1 for neutron stars. And for black holes, there is only mass. There is nothing else in the system. But for neutron stars, the neutron stars can deform each other. One neutron star can deform in the presence of the gravitational field of the others. And this is called a tidal deformation. And one can come up with a parameter called the tidal deformability parameter, which tells us how easy or difficult it is to deform the neutron star. And for each of these neutron stars, there can be a tidal parameter. There can be eccentricity, which I briefly mentioned. So how many parameters do we see here? One. How many over here in the spins? 6. 6, 7, 8, 9, 10, 11. I already see 11 parameters over here. One can make simplifications and make them smaller. Now, these are the parameters of the system, intrinsic parameters. Other than this, there are the extrinsic parameters, which are not the parameters of the system, but they are parameters of essentially of how where the system is located with respect to us, how the system is oriented with respect to us. So essentially, those are the extrinsic parameters. And how many extrinsic parameters are there? Essentially, there are 7 extrinsic parameters. So of the 7 extrinsic parameters, there are 4 space-time coordinates, time, space, 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 3 space coordinates, and 3 Euler angles. 4 space-time coordinates to tell us when and where the event is occurring, and 3 Euler angles to describe the orientation. Of course, instead of working with x, y, and z coordinates, one would work with the distance, area, and depth. Those are 3 spatial coordinates. And instead of working with the Euler angles, one would work with the inclination, which tells us how the source is oriented with respect to the line of observation. And there are two other Euler angles. I don't think I write them here yet. They are called the polarization angle phi, and the phase of coalescence. So I will let me skip this slide for now. It is not very important, at least now. So I'll skip the rest of the slide for now, but summarize essentially that there are quite a few intrinsic parameters. The number can vary depending on the amount of simplification, and there are 7 extrinsic parameters, making it 15 parameters even for binary black holes if you ignore eccentricity, and 17 parameters if you include those tidal parameters which are there in neutron stars. Now, for binary black holes, we almost always ignore eccentricity because it was shown also a long time back in a paper by Peters and Matthews that if you start with an eccentric system, then every time you approach perihelion, gravitational waves are radiated in a way that the system becomes more spherical. So if the system has been evolving for some time, then slowly all the eccentricity is radiated away, and you end up with a circular system. So if a system formed millions of years back, then that system is most definitely circular. However, if a system is only recently formed, then there may be some residual eccentricity. Now, we talked about redshift a lot yesterday, and we are going to talk about redshift in the next lecture. It turns out that our gravitational wave detectors, they are not sensitive to the source frame masses, but something that we call the detector frame masses, which is mass times 1 plus redshift. So we are sensitive not to, this is the mass of the source, but mass times 1 plus redshift. And that is because essentially, you can, if you work with G equal to 1 units, in G equal to 1 units, frequency just scales as 1 over mass. Frequency has the, you are probably more familiar with H equal to 1 units and H equal to 1 units, which we do not use. In H bar equal to 1 units, you know that mass has the dimension of length inverse and has the dimension of time inverse. While for us, the set of units which are appropriate, these set of units are useful in doing quantum mechanics, so we don't use them. We use the G equal to 1 unit. In G equal to 1 units, mass, length, and time, they have the same scaling dimension, and if mass, length, and time have the same scaling dimension, then frequency has to scale as 1 over time, it scales as 1 over mass. So, if you observe a source that is much farther away, so that it's redshifted, it's shifted to lower frequencies just corresponds to higher masses. So essentially what we are sensitive to is not what we are sensitive to is not mass, but mass times 1 plus z, coming from the redshift, which is cosmological. Good. So this we already said that we are sensitive to the phase. We are sensitive to the phase. We see the phase. The phase depends on this redshifted. The phase depends on this redshifted chirp mass. This is not working very well. So the phase depends on the redshifted chirp mass mz, which is m times 1 plus z. He didn't define it on the slide, unfortunately. Maybe for phase. This is my definition of mz. And we are able to measure the redshifted chirp mass very accurately from the phase. We are able to measure the mass ratio to a reasonable degree, however, it's correlated with other parameters. And from the amplitude, we are able to measure a combination of the mass over the distance. The distance was sitting in the denominator out in the amplitude. However, there were these two factors depending on which polarization you were looking at. Note that both these factors, they kind of fall off with iota, and our polarization measurement is not very good. With one single detector, you cannot measure the polarization. You are only sensitive to whatever you observe, some of H plus and H cross. You're not very sensitive to polarization with one detector. Even with 2 or 3 detectors, you are not super sensitive to polarization. So we measure this cosine squared iota kind of poorly, and the distance to a reasonable degree also poorly, that is essentially dominated by this inclination measurement. These are going to become important in the next lecture. Okay, does this answer a part of your question?
Yes, but
Okay, let me now request you to ask your question again.
yes. So my question was whether, like, so here we're considering this binary means. So what if there have been other, like, say, core collapse or some other origins that could generate a similar profile?
Okay, now if you're looking for an inspiral, if you're looking for a very long inspiral, then it's very unlikely that a core collapse or a process like that is going to give you a very long signal that exactly matches a binary inspiral. However, if you're observing a very short signal, if you're observing, which can happen if you're observing a very heavy black hole, a very heavy binary black hole merger, you observe only the last T just ring down only a few cycles, then there it might be difficult for us to say whether it's really the last few cycles before the merger, last few cycles around the merger, or some other process.
Yes, well, statistically speaking, we usually assume that we have both of the sources of this inspired. Yes.
Yeah.
Okay.
Yeah. So here I probably made a statement without explaining what exactly happens. If we observe very massive systems, a very massive system would mean everything is scaled down to lower, everything is scaled to lower frequencies. So the most important thing you need to remember for gravitational wave data analysis is this particular expression, that the frequency scales as 1 over mass. That should be your take-home message. Even if you don't want to remember anything else, then for a very heavy system, the whole waveform gets shifted to lower frequencies, and we know that we are not sensitive to very low frequencies. So we are not sensitive to most of the waveform. We are just left with the last bit of the waveform. And the rest of it we do not see, and this last little bit, which may be maybe the entire waveform was looking like this, which we could observe. It's shifted to lower frequencies, then we are able to observe only this last little bit of 2 cycles. This doesn't tell us really whether it's a inspiraling system or whether it's an explosion, a burst that is happening. Okay. Now, this is a summary of the data analysis workflow for compact binaries. Of course, there's the searches that goes on at which we already talked about a bit earlier, a match filtering process. Now, the match filtering, you can work with the match filtering only with a you can only do a you can only use a certain set of templates for match filtering, right? So you essentially create some kind of a template bank. So here, this is what is known as a template bank. It's every dot on it is a template like this. Every dot on it depends on a set of every point on it is a waveform that has a certain M1 and a certain M2. And of course, you don't do it for the other M1 and M2 because it's essentially the same waveform if you go to the other side, if you reflect this on the other side. So for each of these waveforms, you run this kind of a match, and if your signal is, if the signal that is in there is close enough to one of the templates that you're using, you do see a match. Close enough is an important phrase here. So you do not need to have exactly the same template as there is in the signal. So even if you are approximately correct, you can get a match. Even if you do not have the exact masses, even if you have ignored the spin in the templates, you often do get a match, which is what saves this process. Otherwise, it would not have been possible to run all possible templates. Now, once you have a match, so a match is this kind of a match filtering is useful if one particular template matches not only that signal but also slightly different signals. But that means that with this kind of a mass filtering, you do not really know what masses we're looking at, whether they're really 30 solar mass or 31 solar mass. All of them would have been, all of them would have given the same match. So one wants to do a more rigorous parameter estimation to figure out whether it's 30 solar mass, 31 solar mass, whether it's whether the mass ratio is 1.5, whether the mass ratio is 1.6, exactly which part of the sky the signal is coming from. Also at a very low latency, very soon after the triggers are coming in, some kind of a low latency analysis goes on that sends out a rough sky map which is used to observers used to use for electromagnetic follow-up, but you really want to know exactly what part of the sky this source came from. So one does a more rigorous parameter estimation at high latency, and one estimates essentially all the parameters which we talked about earlier, all the 15 or the 17 parameters, depending on whether it's a binary black hole or a neutron star. And this is not really a course on data analysis. Essentially, one uses Markov chain Monte Carlo-like algorithm or some variation thereof, usually nested sampling, to obtain where the likelihood distribution of the likelihood distribution of the data given all these parameters essentially eventually computes the posterior density on this parameter space given the data and the model, which is GR and the model templates that have gone in. Okay, what goes into the likelihood is again slightly aside for our purpose, but I'd still like to somehow mention that in this likelihood that is constructed here, or what you have in the exponent is some kind of an integral over the frequency of this data minus signal divided the square of the noise. This means that you are dividing by the square of the noise, and the noise is depending on a certain frequency. That means where the noise is lower, you are giving that region a higher weight, while where the noise is higher, you are dividing by a higher number or square of a higher number. So wherever the noise is higher, you are giving that a lower weight. So this is the noise weighted kind of an inner product which goes into this exponent that is used to construct the likelihood over here. So that you, which is appropriate for this kind of a noise power spectral density. Okay. Finally, so essentially this entire game is to find out the posterior density of the parameters given the data, and the parameters, the extrinsic and the intrinsic parameters which we talked about. These are some of the results that you see from the LIGO papers, and I'm highlighting them because all of these results essentially are the posterior density of certain parameters, sometimes a one-dimensional posterior distribution. Here you see a one-dimensional posterior distribution in the distance, in the theta Jn. This is the inclination. J is the angular momentum vector and n is the normal vector. That's why it's called the theta Jn is the angle between the two. That's why the inclination is called theta Jn. So these are one-dimensional posterior distributions. This is the two-dimensional distribution, the 50% and the 90% interval. Here are the various two-dimensional posterior distributions for parameter, for the two mass parameters, the primary and the secondary mass. Once again, the other side is not important. And what you see often as sky localizations, they are also essentially the posterior distribution or contours of the posterior probability density on the 2D sky. And so a quick question. Is a huge patch of a bright color good, or is a tiny patch here good? If you have been following my, if you have been, okay. Let's see. So the idea is, even if you didn't understand all the math that went in, even if we didn't understand all the math that went in, we should still be able to get something out of the figures that come in the that come out in the papers. And these are some of the figures that come out in the papers. Here we are measuring, for example, here we are measuring the masses for this particular detection, which happens to be a neutron star, mass 1 and mass 2. Our measurement lies along this line. That means that we do not know mass 1 and mass 2 for sure. They can be anywhere on this line, but this line has a very narrow width. So it turns, that is because one particular combination of the masses has been very well measured, while the other combination has not been measured. And the combination that has been very well measured has a name, which I happened to have mentioned some time back. Yeah, you have a question? No, but you have an answer.
No, I was trying to answer the previous question.
What was the previous question?
Would we want a smaller than larger? I think smaller.
Yeah, very good. Yeah. So in this case, so the thing is, if you see a white contour in the posterior probability density, so for example, here you see a white contour in the posterior probability density, that means that your estimate is all over the place. Okay? So you do not really know whether the mass is 30 solar mass or 40 solar mass. There's almost 50% probability of it being outside this region between 30 and 40. Okay, in this case, it isn't clear whether this is 50% or what percent. That's because I removed the label of the figure. But if you look at the paper and if you look at the, if you read the caption, then that will tell you what is 50% and whether this is 50% or 68%. But here, this is a very bad estimate because let's say only 50% probability that this that our estimate is in this region. So that means 50% probability that the estimate is outside. Very similarly, this one is a much better estimate. It is over a narrow region, so we have more or less measured that the masses are between this kind of region. However, already you see that one particular combination, it becomes a sharp banana. So that means that one particular combination of masses has been well measured. The other complementary combination has not been measured. The particular combination of masses that is well measured is the chirp mass. That's because to the leading order, we are in the inspiral, we are sensitive to the chirp mass, and here for the neutron star, which is an even lower mass system, we are very, very sensitive to the chirp mass, but not to the other perpendicular parameter. These sky areas, I mean, they often look like bananas out on the sky. If there are huge bananas on the sky, that means that they are all over the place. We do not really know which part of the sky they came from. However, for these loud detections, for these this one GW170814, GW170817, you see very tight contours. That means we know for sure that it was lying in this part of the sky. I think this is another take-home message for this for this part of the lecture, that what we are plotting are posterior probability distributions, and for well-measured quantities, the distributions are, if it's a 2D contour, it's smaller. If it's a 1D distribution, then it's a sharper distribution. Sharper distribution is a better measurement. Okay. Questions? Yeah. I didn't. Okay. 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 So the thing is, see, LVT, the full form is LIGO Virgo trigger, and it was named LIGO Virgo trigger because this is 15, 10, 12. So this came in 2015, 10 October 12th. So this is the first observation run back in 2015, soon after the 150914, which is the first binary black hole detection. So at that point, we were not very sure whether this was a real detection or whether it's something that is fake. So people didn't want to call it a gravitational wave back then. Okay, and this is a plot that came soon after that, or within 1 or 2 years from then. This is a plot that came during O2. So it still retained that name LVT from earlier times. Now it has been replaced by the name GW1510 because now things that pass this kind of a threshold are already surely gravitational waves. Okay, I mentioned threshold, so since we are never sure whether something is a gravitational wave or a fluke, so we have to put in some kind of a false alarm threshold. One can set it. One can say something like, okay, we allow one false detection per year or something, or we can allow 10% probability that it is not astrophysical. One can set some kind of a threshold. So there always has to be threshold, some kind of a threshold. And now this definitely passes that threshold. So that's the question. Yeah.
How can you correlate the G-wave detection with the position on the sky? G-wave.
Correlation between distance and
Correlation between G-wave detection and the position on the sky.
Oh, okay. How do we measure? Essentially, how do we measure how do we know where in the sky a certain gravitational wave came from what we observe, right? Okay. So the leading contribution to where in the sky something is coming from comes from timing. Okay. If one has one detector, then it's not possible to do timing. Things arrive only at a certain time. However, if one has two detectors, then something arrives in one of the detectors at an earlier time, the other detector at a later time. So if one arrives at an earlier time in the other detector at a later time, then you can localize this to what kind of a region? To a circle on the sky, right? And it is this reason you can localize it to a circle on the sky. However, one can do slightly better than timing. One can start measuring subdominant artifacts and make it slightly better than that. But because to the leading order, it's a circle in the sky, you get these huge circular arcs, what I called bananas earlier on the sky. Most of these huge bananas on the sky come from these two detector observations. What you see only with two detectors. As soon as you put in a third detector, you have intersection of three circles, right? So with a third detector, you already go down to 2 points, but it's never really a point. There's always some uncertainty. As soon as you put in a third detector, you get small contours like this. So you asked a very, very important question. Yes.
Which typical time delay we expected between gravitational wave detection and the detection in another electromagnetic wavelength?
In the one, okay, it's difficult for me to answer that. I will talk about this in the next lecture. That for the only detection with an electromagnetic counterpart which we have had, the GRB was observed about 2 seconds after the merger. Now it's exactly what time delays are allowed, or whether we can have some electromagnetic emission even before the gravitational wave chirp. It's very model sensitive and slightly I mean, beyond my expertise to comment on. But I don't think it should be of the order of, it should be of the order of seconds. It should be order of a few seconds on the other side and maybe half a few seconds on the earlier side.
Okay, may I ask one more? Thank you. I saw that in some quasars you observe the active galactic nuclei with supermassive black hole which have very big velocity and fly during this galaxy, and the scientists propose that may this very big velocity of nuclei which are not located in the center of the galaxy due to supermassive black galaxy merger. But what physical condition? It's not symmetrical merger, or why supermassive black hole as a result can
Okay.
go out from the center?
The thing is, you're talking about a very energetic process, right?
Yeah.
So it's, I mean, it's the thing is, if the whole system is perfectly planar, then it's going to remain in a plane. But that it need not be necessarily true, right? Because the system can potentially be, if the system is spinning and the spins are not aligned, the system is potentially precessing, and the system really would be precessing. And if it is precessing, when the gravitational wave is emitted, it is not going to have some kind of a up-down symmetry, right? Gravitational wave can be, a lot of gravitational waves can be emitted in one direction, so it can receive a kick in the other direction to conserve momentum.
Okay, thank you.
Thank you for an interesting lecture. I have a question about redshifted mass. You said we only can detect redshifted mass. We only know redshifted mass. Can we estimate it without the electromagnetic counterpart, or I was just curious because I'm here.
So yeah, redshift, it's a very good question. Redshift can indeed be estimated with an electromagnetic counterpart. That is the that is the entire topic of the next lecture. Okay, thank you. So we are going to hear a lot more about that. Okay, I think we are. You had a question? Okay. We are more or less running out of time. I had a few animations, but I don't want to show the animations because you can easily find the animations on Google and see them yourself. You've probably seen them yourself, and you never know whether the animations they work or not. Yeah, they don't work. So I'll end with the final summary of some key aspects of gravitational wave gravitational waves, and essentially compare them with electromagnetic waves. Remember, I started by comparing Einstein equations to Maxwell's equations. So one important thing that you to note is here we are detecting amplitude and phase. So we are detecting amplitude as opposed to intensity, and in most of electromagnetic astronomy, you detect intensity. If you detect intensity, then that means that if you make a detector that is sensitive by a factor that detects twice the intensity, you make a better detector, then you go to a distance that scales by the intensity goes as the square of the distance. And since the intensity goes as the square of the distance, we increase the intensity by a factor of 2, then your distance reached goes up by a factor of half. And if the distance reached goes up by a factor of half, so sorry, not by a factor of half, if the distance reached goes up by a factor of square root of 2, which is what would happen if the intensity, the sensitivity goes up by a factor of 2, then the number of observations you would see, which essentially scale as the volume, would scale as the sensitivity to the power 3/2. While for amplitude detectors, if you're detecting the amplitudes directly, if you make a detector that is twice as sensitive, you're going to go to a distance reach that is twice as higher, not just square root of 2 times higher, but twice as higher. So that's going to open out a volume that is 8 times bigger. So your sensitivity, the number of observations in gravitational waves actually scale as the cube of the sensitivity, much faster. It's, by building more and more sensitive gravitational wave detectors, you can detect gravitational waves, many more gravitational wave sources than you can do similarly by constructing more and more sensitive electromagnetic detectors. Another important point is we are sensitive to phase and it's in electromagnetic astronomy. In very few cases are we sensitive to phase. Because we are sensitive to phase and we are observing coherent sources, that gives us a lot of power. We can extract the phase, we can use the information from the phase in a number of different ways, which we are going to talk about a lot also in the next lecture. Then gravitational waves are weakly interacting. They were weakly interacting, that made them very difficult to detect. But because they are weakly interacting, they are also very weakly interacting with all the intervening medium. So if you see gravitational waves from very far away, they are not really, they are minimally affected by things like gas and dust, almost not affected at all, and come straight to us. So they can tell us about things that are very far away. One of the biggest drawbacks of gravitational wave astronomy is that we have very poor angular resolution. In most cases, we have much poorer angular resolution than we have for electromagnetic astronomy. And this essentially is because, in some sense, we are observing wavelengths which is of the order of or are greater than the size of the source. While for electromagnetic astronomy, the wavelength is much smaller than the source itself, so it's possible to form a very sharp image. Here we do not really form an image. It's so it's in some sense it is analogous to sound as opposed to light. We do not really hear something. We do not really hear something as coming from a certain point. It's in some sense all over. That's the situation with gravitational waves. So these are some of the key things to remember when we talk about particularly astronomy with gravitational waves. And with this note, I'm going to end this lecture.